Let's start this video by sampling a cosine and then seeing what can go wrong. So let's have ourselves a 1 Hertz signal, same as we had in the previous video, and I'm going to sample that at 5 Hertz. So to be clear, we have cosine of 2 pi times 1 times t, and we're going to sample that at 5 Hertz. And in doing so, as we've already learned, we're going to get 5 samples per period. Okay, it's going to look exactly like that. And if I were to make a table of those samples, that table would look like this. So I would have the sample number and then the value. So the 0th sample is going to be cosine of 0, which is 1. The first sample will be cosine of 2 pi 1 times t. T is 0.2, 0.2. So that'll give me whatever cosine of 0.4 pi is. And I don't need the specific value right now to make this point. Okay, then I'm going to continue that for 2, 3, and 4. Right, let's finish out the period. And let's see, this will give me cosine of 2 pi times 0.4, so that's 0.8 pi. This will be cosine of, let's see, 2 pi times 0.6, so that'll be 1.2 pi. And then finally cosine of 2 pi times 0.8, so that'll be 1.6 pi. Okay, so those are the y values of the first period, and of course, if this is an infinitely long cosine, those go on forever. Now, let's do a different cosine. Instead of starting with a 1 Hertz cosine, suppose we start with a, I don't know, a 1 kilohertz cosine. So let me draw it, and let's switch colors. Oops. So my 1 kilohertz cosine is also going to look like this. So this is cosine of 2 pi times 1 kilohertz, 1000 t. And this I'm going to sample at 5 kilohertz. Okay, 5,000 samples per second, which means that t sub s, the time between samples, is going to be 1/5 of a millisecond. Okay, that's just the reciprocal of f sub s. So I go and I gather my samples, and let's see what I get. My first sample will occur. Let me make myself, a little table here. So this is n, this is value. So my first sample will occur at, actually do that in green, that'll be at cosine of 2 pi 1000 times 0, which is 1. Then my next sample will occur at cosine of 2 pi times, let's see, 1000 times my sampling period, which is 1/5 of a millisecond. And if I notice, stuff starts canceling. So the 1000 and the milli cancel. 1/5 is the same as 0.2, and I'm left with cosine of 0.4 pi. Interesting. Let's continue. Let's do a couple more samples. 2, 3, and 4. This will be cosine of 2 pi 1000 times 2 periods, so 2/5 of a millisecond. So once again, the millisecond will cancel out the 1000, and I'm left with 2 pi times 0.4, or in other words, cosine of 0.8 pi. And I can continue this exercise to find that we're going to get cosine of 1.2 pi and cosine of 1.6 pi. Oh boy, we have an interesting problem on our hands. Let me tell you what's just happened. Okay, this is my 1000 hertz cosine, so the period is a millisecond, and I'm sampling it every fifth of a millisecond. So 1/5, 2/5, 3/5, 4/5, and then the next signal. So look what's happened. I have two very different cosines. I have a 1 hertz cosine on the left and a 1000 hertz cosine on the right. But when I've sampled them, I wound up with exactly the same list of numbers. Okay? Exactly the same list of numbers. If I just give you a table of n and value, you would have no idea of knowing whether or not the signal that I'm looking at originated as a 1 hertz signal or a 1000 hertz signal. Okay? So in other words, giving me x of n by itself is not enough. If I just give you that list of numbers, that's not enough to know whether what we started with, whether x of t was 1 hertz, a kilohertz, like in this example, or, to be honest, any other value or any other frequency. Okay, any frequency you provide me, I can come up with a sampling frequency that would yield the exact same table of numbers. So the upshot is this. The upshot is that if somebody gives you a list of numbers, a list of discrete time signals, you don't really know anything about the underlying continuous time signal that they originated from unless they also provide you with one very important piece of information, and that is they have to give you the sampling frequency. Without the sampling frequency, you have no way of taking that discrete time list of numbers and turning it back into the sound or the radio signal or whatever that you were listening to in the first place. Let me give you an example. Suppose I take a cosine that we can listen to, and in fact we will listen to. Suppose we take an audio signal that's at 500 hertz. So cosine of 2 pi 500t. And let's say I want to sample it with, I don't know, 800 hertz. Sorry, 8,000 hertz. Okay, so let's go through that process. So if I do that, let's see what discrete time frequency I get. So if I do that, I'm going to get a discrete time frequency of 2 pi times 500 over 8,000, which is the same as 2 pi over 16. So that means I'm going to have 16 samples per period. And we know that 16 samples, how long does that take? What is the duration of 16 samples? Well, we know that 16 samples takes 16 over 8,000. Each sample takes 1 over 8,000. 16 of them take 16 over 8,000. So 16 samples takes 16 over 8,000 seconds. So that's how many seconds per period we have. And if we take the reciprocal of that, we get 500. Okay, so that's sort of, it all checks out. So let me show you what I mean by that. Let's go and let's actually listen to this sound. Hopefully this will work with the video. And if we do that, we get the following. So I've already taken the liberty of creating a 1 second signal. So it goes from 1 to 8,000 divided by 8,000. So that's a 1 second signal at 8,000 hertz. And then I've created a cosine at 500 hertz based on that. And if I listen to it, sound scale of x comma 8,000, I get a 500 hertz signal. Okay, let's try that again with the sound turned up all the way. Good. So that worked out well. Now, what if I gave it the wrong sampling frequency? What if I created that signal with 8,000 hertz and then I handed that signal off to you, that list of values, my variable x. Let's say I gave it to you, but I didn't tell you the sampling frequency. Okay, so the same variable x, I'm not changing x. Okay, X is still my list of numbers, but now let's say I forgot to tell you the sampling frequency, or worse yet, let's say I told you the wrong sampling frequency. So let's say I told you the sampling frequency was 16,000, right? So double the original frequency when I created the signal. So let's say you get erroneous information about what the sampling frequency was. So let's see what the effect is. Well, in this case, X still has 16 samples per period because X hasn't changed. But now, because I'm using the wrong sampling frequency, 16 samples, or one period, takes 16 over 16,000 seconds. Okay, so each sample takes 1 over 16,000 seconds. 16 of them takes 1 over 16 over 16,000. So in other words, one period of my signal will now take 1 over 1,000 seconds. And any signal that has a period of 1 over 1,000 seconds has a frequency of 1 kilohertz. Well, now hold on a minute. We started with a 500 hertz signal, but now when I play it back using the wrong sampling frequency, it's going to sound like a 1 kilohertz signal. The frequency is going to appear doubled, even though I didn't change the signal itself. So let's try that. If I go back to MATLAB, we do the following. So let me play this one more time. Now, I'm going to keep X exactly the same, and I'm going to double the sampling frequency that I play it back at. See how different that is? So, the moral of the story is this. If I give you X, if all I do is give you a list of numbers X, you have no way of knowing whether it's a 500 hertz signal or a 1,000 hertz signal, or in fact any frequency. Okay? Any of those answers is correct, and I've demonstrated that by playing back the sound. When I played back the sound, I was able to get with the same list of numbers X, I was able to get a 500 hertz signal and a 1,000 hertz signal. It didn't really make a difference. I didn't have to change X at all. And the resolution of that is that unless you know the sampling frequency, you don't know which is the correct answer. So if I give you a list of numbers X, I have to give you also the sampling frequency that was used to generate X. Without that sampling frequency, you don't know whether I'm talking about a 500 hertz signal or a 1,000 hertz signal or anything for that matter. So the two of them are paired very closely together.